In this question, it says, given the following reaction, what is the expression for Kc? So here, in order to find the expression for Kc, we need to do Kc equals products over reactants. And since this is an elementary reaction that's in equilibrium, and when reactions are in equilibrium, what is equal is the rate of the forward and the rate of the reverse reaction, not necessarily the amount of products and reactants. In fact, they're very rarely equal. We just need to do products over reactants. So this is the concentration of HI, and since there's two of them, we square it, over the reactants, the concentration of hydrogen, times the concentration of iodine, like that. So this is the expression for Kc. It says here, if the equilibrium constant for this reaction is 1 times 10 to the 4, are the products or the reactants favored? Well, if we think about this mathematically, if the equilibrium constant is a big number, so if Kc is equal to, is greater than 1, or if it's a large number, the products are favored. Why? Because products are on the top, so there's more products than there are reactants if Kc equals 1, since it's a ratio. If Kc is less than 1, reactants are favored. And if Kc equals 1, there's an equal amount of both, or neither are favored. And that's basically how it works. So in this case, we have 1 times 10 to the 4 is the value of Kc. That's clearly much larger than 1. So the products are favored to answer this question. It says, what is the equilibrium constant for the reverse reaction? So for the reverse reaction here, we have 2HI gas yields H2 gas plus I2 gas. So we have the reverse reaction. Well, now we have the products of H2 and HI. So the Kc would equal the concentration of H2, concentration of I2, over the concentration of HI squared. Because now the products are the reactants, right? Products become reactants, and the reactants become products. So we turn this upside down. The other way of doing this is the Kc of the reverse equals 1 over the Kc of the forward. So we take the reciprocal. Because we flipped this upside down, we can flip the Kc upside down, which in this case equals 1 over 1.4 times 10 to the 4, which in this case equals 7.14, whoops, times 10 to the minus 5. Notice that now the Kc is much smaller than 1, so the reactants are favored. It's the same reaction. So HI is favored. HI is favored when you write it this way. HI is favored when you write it this way. We just have a different Kc because we wrote the reaction the opposite way. And just so it's clear, it's 7.14 times 10 to the minus 5. And next it says, what is the equilibrium constant for half of the reaction? So that is, for the original reaction, half of an H2 gas plus half of an I2 gas yields, reversibly, instead of 2 now, we have just HI gas. If we half the reaction, then we need to take the Kc to the n. If we doubled it, we would square the Kc. But in this case, we need to take Kc to the 1/2, since we halved the reaction, which is exactly the same as the square root of the Kc. So it's 1.4 times 10 to the 4, all to the 1/2, or the square root. And when you take the square root of this number, you get 118, which is now the Kc value of half the reaction. Note that if you were to double the reaction, you would square this, but if you half it, you take it to the half. If you do it to a third, you take this to the 1/3 power, or you take the cube root, and so on and so forth. That's basically how it works. So, as a reminder, if we reverse the reaction, we take 1 over the Kc to find the Kc of the reverse reaction. If we change the stoichiometric coefficients, we raise the Kc to whatever power we change these by. So if we take half, we raise it to the half. A third, raise it to a third. If we double, triple, we raise this to the 2 or the 3. And that's basically how it works, because these stoichiometric coefficients are used here. So basically you'd have h2 to the half, I2 to the half, and hi to the 1, which is the same thing as taking the square root of all of this, which is exactly what we did.